What if a simple angle could make a bridge safer, a robot move smoother, or a satellite stay pointed at Earth for years? In physics and engineering, angles are never just geometry. They control force, motion, stability, vision, and even how energy flows through a system. Today, let's look at 5 engineering physics angles that seem small on paper, but can completely change how the real world works. First, the angle of repose. This is the steepest angle at which a pile of material like sand, gravel, or grain can stay stable without sliding. Why does it matter? Because engineers use it to design things like conveyor belts, silos, landslide protections, and even roads built on loose soil. The mechanism is simple. Gravity pulls material downward, while friction between particles resists motion. Once the slope gets too steep, gravity wins. A real-world example. If you are designing a storage bin for cement powder, you need to know this angle so the material does not clog or collapse unpredictably. Second, the famous 45-degree launch angle. In ideal physics, launching a projectile at 45 degrees gives the maximum range. But in real engineering, that is only true when air resistance is ignored and launch speed stays constant. So why is this useful? Because engineers still use launch angle analysis in fields like ballistics, sports technology, water fountains, firefighting systems, and mechanical throwers. The mechanism is about splitting velocity into horizontal and vertical parts. A lower angle gives more horizontal speed, a higher angle gives more airtime. 45 degrees is the balance point in the ideal case. For example, if you are designing a machine that throws seeds across a field, or a drone system that deploys objects, choosing the right angle can make a huge difference in distance and accuracy. Third, the angle of incidence. This is the angle at which light, sound, or even a mechanical wave hits a surface. It is important because it determines what happens next: reflection, refraction, absorption, or transmission. That is the physics behind mirrors, camera sensors, solar panels, fiber optics, and laser systems. Mechanically, when a wave arrives at a surface, part of its energy changes direction based on the surface geometry and material properties. Example, solar panels are tilted at a specific angle so they catch more sunlight during the day. Even a small adjustment can improve energy capture a lot over time. Fourth, the angle of attack. This is a huge one in aviation and fluid engineering. It is the angle between a wing or blade and the oncoming air or fluid flow. This angle controls lift. Too low and the wing does not generate enough lift. Too high and you can stall, where airflow separates and lift drops sharply. This is used in airplanes, helicopters, turbines, and even racing car aerodynamics. The mechanism is that changing the angle changes pressure distribution over the surface. That pressure difference creates force. A concrete example: helicopter pilots constantly manage angle of attack to stay stable while hovering, climbing, or turning. Wind turbine blades do the same thing, but in reverse, extracting energy from the wind. Finally, the critical angle. This is the angle where light moving from a denser medium to a less dense one stops refracting outward and instead reflects entirely inside. This is called total internal reflection, and it is the reason fiber optic cables work. Why is that amazing? Because it lets information travel as light through tiny glass strands over huge distances with very little loss. The mechanism is pure wave behavior. Once the incident angle passes the critical value, the wave cannot escape the boundary, so it bounces back inside. That is how the internet can send data quickly across cities and oceans. So angles are not just something you measure with a protractor. They can decide whether a structure stays standing, a wing stays aloft, a solar panel collects power, or a data signal travels across the world. That is the hidden power of engineering physics. The smallest geometric choices can have massive real-world consequences. 5 mind-blowing engineering physics 2 angles that connect science and real-world engineering is just one small part of Physics 2. If you are interested, our full free Physics 2 course is linked in the description.